in this lecture we will talk about the case study on MMC and CHB. We will take two small examples and will design the MMC and the CHB converters. So, let us first start with an MMC for an HVDC application. So, an MMC based AC to DC converter for example, so is used for an HVDC application where the input AC voltage is 420 kV line at 50 hertz and output HVDC voltage is plus minus 320 kV. Okay. The rated power output of the converter is 500 megawatt and the modulation index of each arm is 0.95. Okay. So, let us see how we can design the different components. So, first we decide on the number of cells required, okay. And suppose we choose that okay, there are 3.3 kilovolt IGBTs we will use. Okay. Now, this again depends on experience, like whether you will go with a 3.3 kV IGBT or whether you will go with a 4.5 kV IGBT. So, let us see how this 3.3 kV IGBTs if we use, how does the design go ahead. Now, the DC bus voltage is around 640 kV. So, the number of cells we can choose as the DC bus voltage divided by 3.3 kV by safety factor, which gives us a number of about 330 IGBTs to be used in so 330 number of cells, okay, if we use 3.3 kV IGBTs. So, if there are 330 number of cells, we have taken a safety factor of about 1.7. Okay. That means, yeah. So, we have taken a safety factor of 1.7 here in this equation. Now, redundant cells must be provided in the arms. So, a reasonable estimate can be something like 4 to 5%, right. So, we can choose like about 350 cells in each arm of the MMC. Okay. This can be a starting point in our design, right. Now, if we have 350 cells in each arm, we have about some of them are redundant cells. So, that will be like they will be shut off during the normal operation. Okay. So, like they will be, so only 330 cells will be used at any point of time, right, but the rest cells can be like cold standby. Okay. So, voltage on the DC bus of each cell, if we use 330 cells, the voltage on each cell will be 640 divided by 330. So, 1.94 kV. So, the nominal DC bus voltage on each cell will be close to 2000 volts, right. So, we are using a 3.3 kV IGBT for a DC bus of 2000 volts. Okay. So, we are taking almost a safety factor of like 1.6 or 1.7, close to that value, which is kind of like a reasonable approximation for a first estimate. Okay. So, the nominal DC bus will be like around 2000 volt. So, based on that, the voltage rating of the cell capacitors can be taken close to like 2.5 kV. So, we keep some margin because there will be a ripple on the 2000 volt, and if I take like 5%, if I take about 10% ripple. So, this 2000 volt can go to 2200 volt. So, I can take a rating of the cell capacitors maybe 2.5, maybe someone may take a little bit less or more. So, that can be taken. And then what is the current rating of each device? Now, current rating is this I arm peak, okay, peak current through the device into a safety factor. So, what is the peak current through the MMC? Each arm and that is equal to half of the load current into root 2, half of the load current RMS, this is the RMS load current, half of that into root 2 plus the 1/3 of the DC current. That much of current is flowing in the peak in the arm. So, and then again we have a safety factor. So, how much is the load RMS current? So, if we are transferring power of 500 megawatt, then we can use this formula here and when get about 723 ampere. Okay. So, we can say like 750 ampere of current will is the load current, and what is the DC side current? DC side current is power transferred by E, and the power transferred is this much and the E is this much. So, 781 ampere is the DC side current. So, therefore, the current rating of the device, if you take like this and take a safety factor of 1.2, you get that the current rating of the device is 926 ampere peak, and so you may choose a device of about 1000 ampere IC rating of the IGBT, you can choose about 1000 ampere, okay, close to that value. Okay. So, this will ensure, again we have to be careful like what is the how much is the I square T rating of that device during that 10 microsecond, that must be kept in mind. Okay. Now, next one will be like deciding the cell capacitance, right. Now, suppose we choose a EP value of 40 J per kVA, okay, energy to power that ratio. So, therefore, EC max, okay, the kVA is 500. So, EC max is 400 into 40 into 500. So, 20 megawatt, okay, that much of value, sorry, this is megajoule not megawatt. So, there is mistake here. So, this is 20 megajoule, okay, and EC max as we have seen earlier is 3 times C arm into E square, and so C arm will be equal to EC max by E square and will come out to be 50 microfarad. That is, this value 50 microfarad is the total arm capacitance, effective arm capacitance, right, is equal to 50 microfarad. So, the cell capacitance is related to the arm capacitance by this, because there are n number of cells or n number of capacitors connected in series, right. So, therefore, C cell is n times the C arm, and so if there are 350 number of cells, or anyway this should be have been, so there are 330 number of cells, and we have 50 microfarad. So, a value of roughly 16 millifarad will come, okay. 16 around 16 to 17 millifarad of cell capacitance will be required. Okay. Again, once we have decided this arm capacitance, then we decide the arm inductor value, okay, arm inductor value, and arm inductor value will be can be obtained from this formula here. So, if you put H equal to 2 and omega 314 and C arm as 50 microfarad, the value of the arm inductance is about 20 millihenry. Okay. So, this is how we design the arm inductance, we design the cell capacitance, we design the IGBT, or we can choose the devices. We have to also choose the diodes along with that, and the thyristors we can also choose, which can tolerate the fault condition. Now, I should first say that this kind of a design is not possible in such a short span of time. It requires a dedicated team of engineers and having expertise for many years, working together for several months or years to develop such converters. Anyway, in this short span I will just briefly say what are the basic design ideas that we should keep in mind. Remember, we are only talking here about the electrical aspect, and in a practical design you will have many other aspects like electrical, mechanical, thermal, all these have to be incorporated. We will not go into the other aspects, but we will mostly focus on the electrical part of the converter. So, we have seen this earlier. So, for example, this is the structure of a cascaded edge bridge converter, in which you can see that there are say 5 or 6 cells. So, this diagram is shown with 5 cells here, okay. And this is the input supply, and then there is an extended delta multi winding transformer, and each secondary is connected to a 3 phase diode bridge rectifier which forms the DC link, and then you have the H bridge here, which are then connected in cascade and feeds the motor. Okay. So, very briefly we will see how we can choose components, electrical components in this diagram. So, for example, we have a CHB multilevel converter which is connected to an induction motor driving a pump load. Most of the cases induction motors in the industry are used for driving pumps, compressors, fans, etc., many of them. And another very big application area is the drives application, I mean the motors which are used for say tractions, something like this. So, there is a slight difference between these two applications, because in such drives where you suppose if you have a pump type of drive, then the load torque is proportional to omega squared, whereas in suppose if you are using an induction motor for a traction drive, then the load torque often is independent of the speed. So, the torque requirement and hence the current required from the converter, that will change. In case of pumps, you will require very less torque at low speed, whereas in case of a traction drive you may need the full torque right at or very close to 0 speed. So, there is a difference. Anyway, in this application we are considering a pump load, okay. And so, the parameters of the motor are given as something like 6.6 kV and 5000 HP with an efficiency of 95%, 95.2%, and the motor power factor is 0.88, and the input supply to the transformer is 11 kV. So, these are some of the data given. So, we can make a quick, the first thing is to find out the converter rating. So, how can we know the converter rating? So, the motor input power is 5000 HP. So, and we divide by the efficiency, which is taken as about 95%. So, we see that the motor input power is something very close to 4000 kilowatt. Okay. Now, often these motors can be overloaded by 10%. So, there are several standards which say, for example, a NEMA standard, they say that the motors should perform as means with the full specification if the load torque is 10% over the nominal torque. So, this is often stated. So, in our converter design we can say that the converter is going to be able to supply the motor with 10% overload when the motor is 10% overload. So, we can choose the converter power rating to be about 4.4 megawatt. Okay. Again, this is something which can also vary from design to design. Okay. We are taking very with sufficient margin in our design. Okay. So, the converter power rating should be 4.4 megawatt, because why I said that there can be sufficient. So, when you say overload, then another question may come up is like, for how much duration of overload? Is this 10% overload for 1 minute, or is this 10% overload for continuous operation? So, there generally it is not continuous, it is a short term overload rating. But again, so this will vary from application to application, but we are not going into so much of details of the direct application, and we are doing a simplistic analysis here. Again, I told you we cannot cover such a design in such short span of time. It will require different types of analysis, and also what are the worst case conditions that this design has to withstand. All these factors have to be taken care of. Now, we can choose like an initial guess that the converter power rating should be 4.4 megawatt. So, the converter output VA will be, so converter output power 4.4 megawatt divided by the power factor, and so this will be about 5 MVA. Okay. So, a 5 MVA converter can be chosen to drive such an induction motor, 5 MVA power. So, what is the converter output current? Okay. So, the converter rated voltage is 6.6 kV and 5 MVA. So, about 437 ampere, that is the rated output current of the converter. So, all the switch and diode should be rated for at least 437 into 1.41, that is the this value is the RMS current, and so the peak value is about 617 ampere. So, all the switches and diodes should be rated for at least this value. Okay. So, for the safety purpose, we may choose a switch with a current rating of at least 650 ampere, someone may choose even 700 amperes also. Okay. So, this is kind of like how much margin you can keep in your design. Now, but when you take such a switch, a diode or a IGBT, you should always see the I square T rating of such a switch. It is very important to note that during the fault, the switch should be able to handle the fault current for at least 10 microseconds or even more. Okay. So, the total energy, that is the I square T, during this time maybe 10 microseconds, sometimes going up to 15 microsecond. Okay. Because 10 microsecond is the time before after which the IGBTs will be shut down. Okay. The diodes can continue much more than 10 microsecond, but IGBTs we have to be careful, so that it should have an I square T rating which can sustain the maximum fault current for that much of time, that is 10 microsecond or maybe 15 microsecond. Okay. So, we have to, when you choose the IGBT, you should look into the I square T rating of that. Now, once we have decided on the current rating of the switches, then we look at the voltage rating of the switches. So, the cumulative DC link voltage of the converter, how much is the cumulative DC link voltage? What is cumulative DC link voltage? That is the sum of the DC link voltages of all the cells taken together. Okay. So, that is the cumulative DC link voltage. So, and this, so this we are terming, we are giving a term VDC leg. Okay. So, it is a cumulative voltage, and that is the line voltage times the peak value of the line voltage divided by root 3, so as to get the phase voltage, and M max into 1.15. Okay. M max is the maximum modulation index, and 1.15 is coming because we are using a third harmonic or a space vector PWM modulation technique. So, the value of M max can be taken as 0.95. Again, some user may take it 0.97, 0.98, something like that, but we have kept it 0.95. So, VDC leg cumulative DC link voltage is about 4.9 kV. If we do not use the third harmonic or the triplet harmonics, then we will need additional 15% over 4.9 kV, that is 4.9 into 1.515 will be needed if we do not use the triplet harmonics, if we just use sinusoidal PWM. Okay. So, this is the total DC link voltage, the DC link voltage of or the sum of the DC link voltage of all the cells together. But there is also some other constraints, like the ripple on the capacitor voltage can be taken as 5%. So, there is always a ripple, and this ripple is primarily coming from the fundamental frequency at the input. So, there is a ripple which can be taken as 5%, and the input supply voltage, yes, this is also important, the input supply voltage can have a swell of 15% over the nominal value. So, this is sometimes important because such 11 kilovolt lines sometimes have input surge voltages. Now, this cascaded H bridge converter has uncontrolled rectifier at the input. So, if there is a surge voltage at the 11 kV line, then what can happen is this surge voltage will directly come on the DC link of the H bridge. So, the input supply can also have 15%, and also we have to note that the cumulative DC bus voltage can increase during regenerative braking also. Why? Because when the motor is regenerating, suppose you are braking the motor and it is feeding back the energy, it will come to the DC link and the DC link voltage will go on increasing, because the diode rectifier does not allow the voltage to go back. I mean, not the voltage, the diode rectifier will not allow the energy flow from the DC link into the AC side. Okay. It is an unidirectional device. So, therefore, if there is a regenerative braking, that means the energy is coming from the motor, it will be dumped inside the DC link voltage, and so the DC link voltage will increase in magnitude. Okay. So, often we see that in such CHB or in such diode bridge rectifiers, we have a additional chopper on the DC link, and this additional chopper fires once the DC link voltage goes above a certain predefined magnitude. Say if the DC link voltage goes beyond 20 to 30% of the nominal value, then the chopper is fired, because otherwise it will destroy the switches in the which are connected to the DC link and a part of the H bridge. Okay. So, if you see the above constraints, then we can say that it may be a good choice, or it may be a starting point, or it may be a starting choice to consider that the nominal DC link voltage is about 5.5 kV. Okay. So, I am taking about 10% more than this value. So, 5.5 kV is the cumulative DC link voltage, and the individual cells, suppose we take 6 cells in each leg. So, the cell voltage is therefore this 5.5 kV divided by 6, that is about 916 volt, okay, the DC link voltage. So, voltage rating of the switch can be taken as a safety factor into VDC, and if you take a safety factor of 1.8, then we see that the devices are about 1700 volt IGBTs and diodes. Okay. So, 1700 volt IGBT or diodes are quite frequently available, okay, at this power, at this voltage and at the current rating which we have talked about. Now, why did I choose 1.8 as the safety factor? Now, this is again depends on the designer. Okay. As I told you, this DC link voltage will vary during the operation of the converter, but I will also say that the DC link voltage. So, when you run such a converter, there may be several types of possibilities while running this converter. Often you will see, for example, this converter is used for a long cable application. Now, when you have a long cable application, it may happen that there will be voltage reflection, because the cable and because the inverter and the or the converter and the motor may be far away from each other. Okay. In a long cable, suppose in a mining application, then what will happen is there will be voltage reflection from the motor. Generally that is less in multi-level converters, but still voltage reflection is something which a user should be aware of or a designer should be aware of. And so, because of that voltage reflection, you would like to keep some margin on the DC bus. Okay. So, this is one reason why we have kept 1.8, and also momentarily, for example, you have a bypassing happening in the DC link, and during the process of bypassing or during the process where the IGBTs are getting shut off, you may find that the DC link voltages are temporarily increasing. I mean, the devices are subjected to a voltage of more than the rated voltage of 916 volt. So, for these reasons, this safety factor of 1.8 has been taken. Many designers, suppose you are working in a harsh environment, many designers will take a safety factor of maybe 2, maybe even more, and so we are just giving you a starting point for the design. Okay. So, the voltage rating of the switch we have taken like similar to 1700 volt. So, for this rating of 1700 volt and 650 ampere, you find, if you go to the websites, you find there are several manufacturers like Infineon, Semicron, Mitsubishi, iAxis, many other manufacturers are there. So, you can go to their websites and you will find these kind of switches. You can see their properties, the data sheet of these switches, and can see and can also see their application notes, and you will find a lot of information how to use those switches. Okay. Now, the other thing is the diode voltage rating for the rectifiers. So, we are now thinking about the input side diode bridge rectifier. Okay. Again, the diode voltage rating is the safety factor into the line voltage. Okay. Now, if you want to produce a DC bus about 916 volt, the input rectifier side AC line voltage is about 678 volt RMS, because the DC bus voltage with such a rectifiers is about 1.35 times the AC RMS line voltage. Okay. This information you can see in any power electronics textbook, the rectifier section, and you will find this information that it is about 1.35 times. So, we are not going into that details. Now, so the nominal voltage rating of the diode is close to about 1000 volt. Again, the considering all these safety factors into account, a diode of about 1600 or 1700 volt, this kind of a diode can be chosen. Okay, the voltage rating of the diode. And then we can also see what is the current rating of the diode for the rectifier. So, the output power rating of the converter is like close to 4.4 megawatt. So, the output power is equally distributed in each cell, we are assuming it is getting equally distributed. So, the power of each cell is about 245 kilowatt. So, this is the, so there are 18 power cells, because there are 6 power cells in each leg and there are 3 phases. So, we have 18 power cells. So, the each cell handles a power of about 245 kilowatt. So, if the efficiency of the power cell is about 98%, so the input power to the each cell is about 250 kilowatt. Okay. Now, the output power of the rectifier is equal to VDC into IDC, which you can again write in terms of the input quantities as VDC into IDC is equal to, this is the 250 kilowatt, this is the output power. Okay, then input this is the input power of each cell, VDC into IDC is 250 into 10 to the power 3, and which is again equal to 1.35 VLL into IS1 by 0.78 into 0.95. How do we get this one? Again we get this factor from the analysis of 3 phase rectifiers. The fundamental source current is 0.78 times the DC current. You can see this one in any power electronics book, the rectifier section, and the DPF is like 0.95, okay, displacement power factor is 0.95. So, by substituting these values here, we get that the input side fundamental input current is about 224 ampere, and the average diode input current will be 2 by pi times this IS1, that is about 142 ampere. So, this is the IF average, the average diode current 142 ampere. This is what is given in the data sheet of diode rectifiers, and accordingly you can choose which diode to use. Okay. Again, the diodes have to bear the short circuit current, accidental short circuit current, and the diode surge current IFSM should be high enough. Okay. Again, IFSM of diodes are very high. So, diodes and thyristors both have this surge current rating very high as compared to, for example, IGBTs. So, this is something which favors the diodes, and rectifier class of diodes have been used frequently because they can sustain the short circuit current. So, remember this I square T rating also you should check. And then with this VRM and ID of this one, you can see many manufacturers 1600 volt and 150 ampere rating. So, Semicron, Mitsubishi, IGBT, Infineon and other manufacturers, ST and there are many other manufacturers. You can just have a look into the websites. And what about the multipulse transformer? Multiple transformer, number of rectifiers to be used is 6. Okay. There are 6. So, there are secondary windings is 6. The phase shift required in the secondary windings is 10 degrees, which we have covered earlier also. The primary voltage is 11 kV, secondary voltage is 678 voltage, because the DC link of each cell is around 916 volt. So, then you can decide what is the transformer turns ratio. So, the primary is 11 kV line to line and secondary is 670 volt line to line. Okay. So, you can now decide what is the value of N1 is to N2. However, this transformer design is not so easy, it is quite a complicated transformer with one primary and 6 secondaries. Also these 6 secondaries are connected in extended delta, and it will take time. I mean, this transformer designing is complicated, and also there are several tests. So, this is not a standard transformer, and several tests have to be performed on this transformer, so as to get the accurate, so how much is the input current cancellation, how much are the forces on the transformer during short circuit. There are many tests which has to be performed on this transformer. Okay. So, it is an elaborate arrangement here. And coming to the efficiency, what is the efficiency? The transformer efficiency is close to about 98%. Okay. Again, this is very rough approximation, and then the power electronics section of the converter has an efficiency of about 98 to 99% of efficiency. So, the overall the converter efficiency input to output, like from the transformer primary and going to the motor, the overall converter efficiency is more than 96%. Okay. So, this is what generally the cascaded edge bridge converters, they are operating in this efficiency range. Okay. In spite of having so many components, and in spite of having such an elaborate transformer and so many devices working together, it is actually surprising to note that the efficiency is quite high in fact. And one of the reasons, as I told you before also, one of the reasons why the efficiency should be high is that they are processing a large amount of power. So, even this 3 or 4% of loss is substantial loss, which will appear as heat inside the converter and has to be dissipated out. So, the efficiency of such multi-level converters like cascaded edge bridge may be 97% or something like that. MMC for HVDC application, they are having an efficiency of more than 99%. Okay. So, these are some of the range of efficiency which we encounter in such multi-level converters. Okay. So, this then forms this is again as I told you, this is a very basic guideline and maybe just a starting point of your design, but much more analysis needs to be done on this, lot of analysis, design iterations, and then again a lot of testing has to be done. So, it will take a long time to with a dedicated team to perform the whole design, fabricate it and then run the converter. So, I have just given you a basic starting point as part of the course here.